130 million light-years away, two dead stars met for the last time and Earth felt the collision as a faint tremble in space-time. Less than 2 seconds later, a flash of gamma rays crossed the sky. Then came the fading glow blue at first, then red, carrying the quiet evidence of something extraordinary. Gold, platinum, uranium, some of the heaviest elements in nature may be born in moments like this, from the wreckage of neutron stars. Welcome to Boring Science Stories. If this kind of calm cosmic science helps you relax, study, or drift towards sleep, please like the video, subscribe to the channel, and share it with someone who loves the mysteries of space. Thank you for spending your time here. What time is it where you are? And where are you watching or listening from? Leave a comment below. Now, let us begin with the first ripples from a distant collision. The first clue does not arrive as light. It reaches Earth as a change in distance so small that ordinary measurement would lose it entirely. A passing strain in space and time produced far beyond the Milky Way. At the advanced LIGO observatories in Louisiana and Washington, long tunnels hold laser beams that travel back and forth between mirrors, waiting for one arm of the detector to stretch, while the other shortens by an amount far smaller than an atomic nucleus. This is the scale at which gravitational waves become visible to instruments, not as a picture in a telescope, but as a pattern in motion. The idea behind them comes from general relativity, the theory in which gravity is not simply a force pulling objects together, but the shaping of space and time by mass and energy. When massive objects accelerate violently, that shape can ripple outward. The ripple weakens as it crosses the universe, yet it carries a record of what made it, for most of human history. Astronomy depended on light and other forms of electromagnetic radiation. Stars, galaxies, nebulae, and explosions announced themselves by sending photons across space. Gravitational waves opened a different path. They could pass through dust, gas, and darkness without needing a clear line of sight. They carried information from places where light might be delayed, absorbed, or never released at all. The first direct detection came in 2015, when LIGO recorded the merger of two black holes. The signal was brief, rising in frequency and strength, before ending abruptly as the two objects became one. It confirmed that gravitational waves were not only a prediction on paper, but a measurable part of the universe. It also showed that instruments on Earth could detect events so distant and compressed that no ordinary telescope could have watched the central moment. The black holes had no surface from which light would shine in a simple way. Their final orbit and merger were therefore announced mainly by gravity itself. That discovery changed the position of LIGO in astronomy. It was no longer only a physics experiment testing a famous theory. It became an observatory, one that listened for changes in the structure of space itself and translated them into information about hidden collisions. Each passing wave slightly changed the length of the detector arms. Computers compared the signal to models of possible events, searching for the shape expected from compact objects in orbit. The result was a new kind of evidence, one that did not depend on brightness. A dark event could still become known if it shook space and time in the right way. This mattered because the universe contains many objects whose most important behavior is gravitational rather than luminous. Black holes are the clearest example, but neutron stars belong to the same class of extreme remnants. They are small by stellar standards, yet their mass is packed into a region roughly the size of a city. Their gravity is intense, their matter is dense beyond ordinary experience, and their orbits can become laboratories for physics that cannot be reproduced on Earth. Before the first kilonova was identified in detail, LIGO had already shown that compact objects could be studied through their final motion. The instrument did not need to resolve the objects visually. It read the changing rhythm of their orbit, As two massive bodies circle one another, they lose energy by emitting gravitational waves. That loss is usually very slow, but during the final stages it becomes rapid. The orbit tightens, the motion accelerates, and the emitted waves rise in pitch and amplitude. The form of the signal reveals the combined mass of the system and the way the objects move under extreme gravity. In that sense, the detector receives not a simple alarm but a trace of the final seconds or minutes of a cosmic system. The challenge is that the signal reaches Earth buried beneath many other sources of noise. The planet trembles, human machinery vibrates, air moves. Even the detector itself has tiny sources of disturbance. LIGO works by controlling, measuring, and filtering these effects until the remaining pattern can be tested against the expected form of a gravitational wave. This makes the detection process careful and patient. A signal must appear in more than one observatory at nearly the right time, with a matching shape. Only then can it be treated as evidence from space rather than a local disturbance. The 2015 black hole event passed that test and became the first direct proof of a method that had taken decades to build. Its importance lay not only in confirming Einstein, it showed that the universe could be observed through gravity in a practical way. Once that was true, a larger question opened. If black holes could be heard, then other compact collisions might also leave their own signatures. Neutron stars were especially important because they are not completely dark. Unlike black holes, they contain matter with a surface and internal structure. When two neutron stars spiral together, their collision should disturb space and time, but it should also throw material outward and create light. That combination would allow astronomers to compare two kinds of evidence from the same event. Gravity would describe the motion of the dense cores. Light would describe the matter released after impact. The possibility was powerful because each signal would correct the limitations of the other. Gravitational waves can identify the masses and orbital behavior of the merging objects, but they do not by themselves show the chemical aftermath in detail. Light can reveal temperature, composition, and expansion, but it can miss the earliest hidden motion that caused the explosion. Together, they could turn a distant collision into a fuller physical story. In the years after the first detection, this possibility remained more than an abstract hope. Observatories around the world prepared for alerts from LIGO and its partners. When a promising gravitational wave signal appeared, telescopes could be directed toward the likely region of sky. The difficulty was that gravitational wave detectors do not point with the precision of optical telescopes. They provide a broad area where the source may be located, narrowed by the timing and strength of the signal at different sites. Astronomers then need to search that region for a new point of light, a source that was not visible before and that changes quickly. This search requires coordination, speed, and patience. A transient event can fade within days. Important color changes can happen even sooner. The first ripples therefore carry urgency, not because they are loud, but because they mark the beginning of a short window in which the universe is still displaying the visible consequence of the collision. This is where gravitational wave astronomy begins to differ from older forms of discovery. A telescope often starts with light and asks what produced it. LIGO can start with motion in space and time, then invite telescopes to look for the light that follows. The order of evidence changes. The hidden event announces itself first through gravity, and the visible sky becomes a second stage of investigation. That shift is essential to the story of kilonovas. A kilonova is not only an explosion seen in space. It is an event whose meaning depends on connecting the inward spiral of compact stars with the outward release of matter. Without gravitational waves, the light alone might be classified as a strange transient among many others. Without light, The gravitational wave would reveal a merger but not the full chemical and energetic aftermath. The two together create a stronger account than either one could carry alone. Before that count could be tested, the instruments had to prove that the faintest distortions could be separated from earthly noise. The success of the black hole detection made that confidence possible. It showed that the final motion of massive compact bodies leaves a signal with a recognizable structure. It showed that distance does not erase information completely. It showed that a collision hidden from view can still be reconstructed from the wave it sends through space and time. In this way, the first ripples prepared the ground for everything that followed. They made it possible to treat the universe not only as something seen, but as something measured through the changing geometry of space. The later neutron star event would add light, colour, matter, and chemistry to that method. But the doorway opened first with a nearly invisible stretch in LIGO's arms. A small change recorded on Earth from a violent source far away. The detector did not show an image of the event. It provided the first part of a sequence, the gravitational signature of bodies moving under extreme conditions. From that point onward, the question was no longer whether space and time could carry news of distant collisions. The question became what kinds of collisions would speak through them next, and whether the next signal would bring light with it. The August event begins differently from the black hole signals that came before it. In the data, the pattern does not rise and vanish almost at once. It lingers. For more than 100 seconds, the detectors record a steadily tightening rhythm, the mark of two compact objects circling each other many times before the final crash. That longer duration immediately narrows the possibilities, because the length of a gravitational wave signal depends strongly on the masses of the objects that produce it. Heavy black holes complete their final observable dance quickly. Lighter compact objects can remain in the sensitive range of the detector for much longer, tracing a more extended spiral before merger. The signal detected in August 2017 therefore carries a different kind of weight. It is not the brief ending of two massive black holes. It is the drawn-out final approach of something smaller, denser, and made of matter. The event is later known as GW 170817, a name built from the date of detection, but the name is less important than the change it represents. The waveform tells physicists that the source is a binary system, two objects locked in orbit. It also suggests that each object has a mass close to what is expected for a neutron star. This matters because a neutron star is not merely a small star. It is the collapsed core left behind after a massive star explodes and sheds its outer layers. What remains is so compressed that protons and electrons are forced into neutrons across much of the interior, creating matter at densities close to those found inside atomic nuclei. A teaspoon of such material, if it could be isolated in ordinary conditions, would have an enormous mass. The surface gravity is immense. The interior pressure is beyond direct laboratory testing. Yet in a binary system, two neutron stars can become visible to gravitational wave detectors because their orbital motion is controlled by that density and mass. Each orbit emits a little energy as gravitational waves. Over long spans of time, the orbit shrinks. The stars draw inward, not because they collide immediately, but because the system slowly pays away its orbital energy into space itself. By the time the signal reaches the frequency range that LIGO can measure, the end is close. The two stars are moving rapidly, their separation is falling, and the wave pattern becomes a record of the last stage of their shared motion. The August signal is strange not because it violates expectation, but because it matches a long-awaited expectation too well to ignore. For decades, neutron star mergers had been proposed as sources of gravitational waves and as engines for short gamma-ray bursts. Pulsars in binary systems had already shown that compact orbits decay in a way consistent with gravitational wave emission. The evidence was indirect but strong. What had been missing was the final merger itself, captured as it happened. The detection brings that hidden ending into view through gravity. In the first stage of analysis, the exact nature of the objects cannot be declared from one clue alone. But the signal's mass range makes the neutron star interpretation compelling. The objects are too light for the black hole mergers already observed by LIGO, and they fall into the mass range known from neutron stars in the Milky Way. At the same time, their collision should not be silent in light. Unlike black holes, neutron stars have material surfaces. When they meet, matter can be torn away, heated, shocked, and expelled. The gravitational wave therefore does more than announce a merger. It suggests that a visible counterpart may exist somewhere in the sky, fading even as the signal is being studied. The shape of the waveform also contains a quieter scientific problem. Neutron stars are not perfect points. They have structure. As two such stars approach, each one can deform the other through tidal forces, the same general kind of gravitational stretching that raises tides on Earth, but under far more extreme conditions. The amount of deformation depends on how stiff or soft neutron star matter is. A star with a stiffer interior resists compression differently from one whose matter gives way more easily. This means that the last orbits may carry traces of nuclear physics, not in a laboratory sample, but in the motion of entire collapsed stars. The Auger signal is not strong enough to answer every question about that interior, yet it begins to connect gravitational astronomy with the deep uncertainty of matter at extreme density. It indicates that the objects are compact and light enough to be neutron stars, and it places broad limits on how large and deformable they can be. The collision is therefore both an astronomical event and a physics experiment conducted by nature. The contrast with the first black hole detection remains important. In a black hole merger, the objects have no solid surface, no ejected crust, and no ordinary matter outside the event horizons, unless surrounding gas happens to be present. The gravitational waves carry most of the direct information about the merger. With neutron stars, the same final motion can lead into a much richer aftermath. The stars do not simply disappear into a mathematical boundary. Their matter collides. Some of it may fall inward immediately. Some may form a disk around the newly formed remnant. Some may be thrown outward at a significant fraction of the speed of light. This difference is already implied before any telescope sees the glow. The longer signal is the first hint that the universe is offering a merger where matter matters. It is a slower spiral because the bodies are lighter. It is a more revealing spiral because their surfaces and interiors can influence what follows. It is a different signal because its end is not only a gravitational event but the beginning of an electromagnetic one. The location of the source is first known only imperfectly. Gravitational wave detectors can compare the arrival times at different sites and use the shape and strength of the signal to narrow the region. But the patch of sky remains large by the standards of optical astronomy. Even so, the signal gives enough warning that astronomers can begin searching. Its duration also has a practical consequence. A long spiral allows the detection systems to gather more cycles of the waveform, giving more information about the source than a very short burst would provide. The chirp, as physicists often call the rising pattern, is not a sound in space, but it can be translated into sound because its frequency rises in a way that resembles an audible sweep. That translation is useful only as an aid. The real evidence is numerical, measured by changing laser paths and matched against predicted waveforms. Still, the idea of a long chirp captures something physically true. The system spends its final observable time accelerating, releasing energy faster and faster until the two objects can no longer remain separate. The signal then ends in a region where the physics becomes more complicated. The merger remnant may be a heavier neutron star for a short time, or it may collapse quickly into a black hole. The gravitational wave detectors are most sensitive to the inspiral, so the late aftermath is harder to read directly from gravity alone. This leaves space for light to take over. The early signal identifies the event as a likely neutron star merger. The sky must then be searched for the glow produced by expelled material. That division of labour is central to the discovery. Gravity gives the first diagnosis. Light can show the wound left behind. The importance of the august event lies in this transition from suspicion to pursuit. Within the data, scientists see the kind of signal that had been anticipated but not yet observed, long-lasting, relatively low in mass, and consistent with two neutron stars losing their final orbital support. It is not merely another entry in the catalogue of compact mergers. It is the first sign that a different branch of violent astronomy has opened. The signal says that matter has been brought into conditions where density, gravity, heat, and nuclear reactions may all become part of the same story. The event is still distant, associated with a galaxy about 130 million light-years away, but the distance does not make it abstract. The wave preserves the timing of the final inward spiral with enough clarity to distinguish it from previous black hole collisions. That distinction is the doorway to everything that follows. Before the gamma rays arrive in the account, before telescopes isolate the fading source, before spectra reveal heavy elements, the long gravitational wave already changes the question. It tells observers that the universe has not sent only another dark merger. It has sent a collision where compact matter may have been torn open, where light may have been produced, and where the aftermath may carry chemical evidence that gravity alone could never provide. The gamma-ray signal arrives almost immediately after the gravitational wave, and its timing changes the meaning of the event. Less than 2 seconds after the merger signal reaches Earth, a space-based gamma-ray telescope records a short flash from a broadly consistent region of the sky. Gamma rays are the highest energy form of light, produced in some of the most violent environments known in astronomy. They do not show the merger remnant directly, but they provide a fast and important clue. For many years, short gamma-ray bursts had been linked in theory to the collision of neutron stars, yet the connection had remained difficult to prove. These bursts last only a brief time, and their locations can be uncertain. Some occur in distant galaxies, too far away for a detailed view of the aftermath. The August event provides something different. The gravitational wave arrives first as evidence of two compact objects spiraling together, and then the gamma-ray flash follows from the same general direction. The gap is small enough to make chance coincidence unlikely, and the pairing is exactly the kind of evidence astronomers had been waiting for. A gravitational signal identifies the merger. A burst of high-energy light suggests that the collision also launches a powerful outflow. The event is no longer only a disturbance in space and time. It has become a source of radiation, and that radiation begins the search for the visible remnant. The reason this matters reaches back to a long-standing problem in high-energy astronomy. Gamma-ray bursts were first discovered as sudden flashes from the sky, brief and intense, with no obvious steady source. Over time, astronomers learned that there are two broad classes. Long bursts are usually connected with the deaths of massive stars and the formation of black holes in collapsing stellar cores. Short bursts, lasting only a small number of seconds or less, remained more difficult to secure. Their brevity made them harder to localize, and their engines were hidden behind rapid expansion, extreme heat, and narrow beams of radiation. A merger of neutron stars offered a plausible engine because it could produce both a compact remnant and a disk of hot material feeding inward. Under the right conditions, some of that energy could be directed into narrow jets moving close to the speed of light. If one of those jets points near Earth, The gamma-ray flash can appear bright and brief. If the viewing angle is wider, the flash may be weaker, delayed, or partly hidden. The August flash is relatively faint compared with many short gamma-ray bursts, and that detail becomes part of the interpretation. It suggests that Earth may not be looking straight down the strongest part of the jet, or that the outflow has a more complex structure than a simple narrow beam. The gamma rays therefore do not close the case by themselves, they sharpen it. They show that the merger produces high-energy radiation, but they also force astronomers to consider geometry, orientation, and the behavior of matter moving at relativistic speeds. In this way, the flash becomes more than a confirmation. It becomes a constraint on the shape of the explosion. The instruments that detect gamma rays work very differently from LIGO. They orbit above the atmosphere because Earth's air blocks most gamma rays from reaching the ground. Their detectors do not usually form sharp images like ordinary cameras. Instead, they measure incoming high-energy photons and estimate where they came from across a broad region. In the August event, this limitation is balanced by the gravitational wave detection. Each messenger has a weakness. LIGO can recognize the merger but begins with a wide sky area. Gamma-ray detectors can mark the presence of a high-energy flash, but may also have a large uncertainty in position. When the two signals overlap in time and direction, the combined evidence becomes stronger than either signal alone. The gravitational wave says that compact bodies have merged. The gamma-ray flash says that light emerged almost at once. The small delay between them is physically meaningful, but it has to be handled with care. It may include the time needed for the outflow to form, break through surrounding material, and release radiation that can escape. It may also reflect the direction from which the event is viewed. The important point is not that gravity and light leave the source in exactly the same way. They do not. Gravitational waves come from the motion of the dense cores during the final in-spiral. Gamma rays come from energetic material outside the newly formed central object. Their near arrival together tells astronomers that these processes are closely linked in time, even though they arise from different parts of the event. The pairing also provides a remarkable test of basic physics. Gravitational waves and gamma rays travel across roughly 130 million light-years before reaching Earth, yet they arrive separated by only a very small interval on that long journey. Most of that delay is likely produced at the source rather than during travel. This means the observation supports the idea that gravitational waves move at essentially the speed of light, within very tight limits. A distant merger thus becomes not only evidence for kilonovas, but also a check on how gravity itself propagates through the universe. The event links extreme astrophysics with fundamental physics in one observation. The gamma-ray flash also changes the human tempo of the discovery. A gravitational wave alert alone can tell observatories that something important may have happened. But the addition of gamma rays adds urgency and direction. It suggests that the source is not a black hole merger with no obvious light, but a neutron star event that may soon reveal a fading glow. The high-energy flash is brief. The optical and infrared light will last longer, but not indefinitely. Astronomers need to locate the source before it dims and before the earliest color changes are lost. The gamma rays therefore serve as a second alarm. They do not provide the full map, but they narrow the nature of the event. They tell the astronomical community that the sky should be searched for a new transient in a nearby galaxy within the gravitational wave region. That search will soon lead to a source in NGC 4993, a galaxy in the constellation Hydra. But at this moment in the sequence, the essential change has already happened. The event has crossed from one messenger to two. The word messenger has a specific meaning here. It refers to different carriers of information from the same astrophysical source. Light is one messenger. Gravitational waves are another. Neutrinos can also act as messengers in other kinds of events. Though they are not the central evidence in this kilonova, For most of modern astronomy, electromagnetic radiation carried nearly all the information. It arrived as radio waves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays, each revealing different temperatures and processes. Gravitational waves add a new channel because they come directly from the motion of the mass under strong gravity. The august event is extraordinary because the channels are not separate discoveries about different objects. They are connected signals from one collision. This allows the same event to be read from the inside outward. Gravity records the inward spiral. Gamma rays reveal that an energetic outflow follows. Later, other wavelengths will trace the expanding debris and the formation of heavy elements. The gamma ray flash stands at the hinge between those stages. It is too brief to explain the whole event, but it proves that the merger is not confined to the hidden core. Energy escapes quickly. Matter outside the remnant is organized enough, or disturbed enough, to produce high-energy radiation. That outward release makes the later glow physically plausible. It also supports the long-suspected link between neutron star mergers and short gamma-ray bursts, while showing that the relationship can be shaped by viewing angle and surrounding debris. The event does not reduce the subject to one simple model. It makes the model more testable. From this point forward, the collision has a location to be narrowed, a source type to be examined, and a chain of emissions to be followed as they cool. The gamma-ray flash is not the kilonova itself, but it is the first light connected to the merger. It marks the moment when the silent information of gravity begins to join the visible universe. The next task is to find where that light is coming from, to turn a broad alert into a precise point, and to watch the fading source before its most important clues spread into darkness. The search after the gamma-ray flash becomes a coordinated act of narrowing. A gravitational wave signal has marked a merger, and a burst of gamma rays has shown that high-energy light escaped almost at once. But neither messenger gives astronomers a precise image of the source. The sky area remains too wide for one telescope simply to stare at a single point and find the answer. It has to be searched, field by field, galaxy by galaxy, while the new source is still bright enough to show its early behavior. This is where the event changes from a detection into a campaign. Observatories on the ground and in space begin working with different strengths, not all trying to measure the same thing, but each trying to capture one part of a rapidly fading physical process. Wide-field optical telescopes look for a new point of light that was absent in earlier images. Infrared instruments prepare to follow cooler material after the first blue light declines. Ultraviolet telescopes search for the hottest early emission. Radio and X-ray observatories wait for signs that fast-moving debris is colliding with surrounding gas. The merger is no longer a single signal. It is becoming a sequence, and the sequence must be caught before it changes beyond recognition. The practical challenge is considerable. The gravitational wave region covers many possible locations, and the source is expected to fade over days, not remain steady like a star. Astronomers compare fresh images with older surveys, looking for something new beside the steady background of galaxies and foreground stars. A true counterpart should appear in the right part of the sky, change quickly, and sit at a distance consistent with the gravitational wave estimate. False leads are possible. Variable stars, supernovae, active galactic nuclei, and minor solar system objects can complicate the search. The strongest candidate has to satisfy several conditions at once. It must be new. It must be fading. Its colours must evolve in an unusual way. It must lie in a plausible host galaxy. Within hours, a promising source is found near the galaxy NGC 4993, an elliptical galaxy in the constellation Hydra, roughly 130 million light-years from Earth. This distance is large in everyday terms, yet close enough by cosmological standards for many telescopes to study the event in detail. The location turns a broad alert into a specific object. Once the counterpart is identified, the task changes again. The question is no longer only where the event happened, but what kind of light it is producing, and how that light changes with time. The first optical detections show a transient source that is bright enough to observe but already evolving. It does not behave like an ordinary supernova. Its early blue light fades quickly, and redder wavelengths become more important as the debris expands and cools. This fast color evolution is one of the earliest signs that the event belongs to a different class. The source is given names in different observing programs, but its physical interpretation begins to converge around the same idea. The merger has produced a kilonova, a glow powered by radioactive decay in neutron-rich material thrown out during and after the collision. The term kilonova reflects a brightness between classical novae and supernovae, but the label is less important than the mechanism. This is not a star blowing off surface layers in a repeating outburst, and it is not the collapse of one massive stellar core. It is the aftermath of two dense remnants disrupting each other and ejecting matter that can build heavy atomic nuclei. The worldwide observing effort matters because no single wavelength can carry the full story. Visible light reveals the early brightness and color. Infrared light becomes crucial as heavier elements absorb shorter wavelengths and shift the escaping radiation toward redder bands. Ultraviolet observations provide information about the hottest and least opaque material in the first stage. Spectroscopy, the technique of spreading light into its component wavelengths, gives a way to infer composition and motion. Although the spectra of kilonova debris are difficult to interpret because heavy elements create many overlapping absorption features, X-rays and radio waves, appearing later, help trace the interaction between fast outflows and the environment around the merger. Each measurement is incomplete by itself, but together they form a time-resolved portrait of a system expanding outward from the collision. This is the central strength of multi-messenger astronomy. It does not simply add more observations. It allows different kinds of evidence to be placed into a single physical order. The gravitational wave comes from the inspiral. The gamma rays point to a brief relativistic outflow. The optical and infrared glow trace slower, heavier, ejecta. Later high energy and radio emission reveal how some of the fastest material moves through surrounding space. Instead of one mystery with one clue, the event becomes a layered reconstruction. The timing of each signal matters, as does its color, brightness, and duration. The galaxy association matters as well, because the host environment gives context. NGC 4993 is not a region filled with massive young stars, the kind often linked to long gamma-ray bursts. It is an older galaxy where neutron star binaries can survive for long periods before finally merging. That setting supports the interpretation that the source comes from the delayed end of an old stellar system, rather than the immediate death of a newly formed massive star. The discovery also shows why preparation before the event was so important. The alert network, telescope scheduling, comparison images, and data sharing channels had to function quickly enough to make the early observations possible. A kilonova changes too fast for a slow response. Its earliest colors and brightness carry information about the amount of material ejected, its velocity, and its composition. Missing the first night would not destroy the discovery, but it would erase part of the evidence needed to separate models. The first hours are especially valuable because they may include emission from material with fewer heavy elements and lower opacity, meaning light can escape more easily. As the debris expands and radioactive decay heats it from within, the opacity changes the way the glow appears. The transition from early blue light to later red and infrared light is not just a visual detail. It is a record of the ejector becoming transparent or opaque in different ways, depending on what was forged inside it. The global campaign therefore turns changing light into a physical measurement. It asks how much mass was expelled, how quickly it moved, whether the debris came from tidal stripping, shock heating, winds from an accretion disk, or several channels at once. Those distinctions matter because they connect the visible kilonova to the hidden merger dynamics. Material torn from the outer parts of the neutron stars may have a different neutron content from matter blown out after the remnant forms. Some ejecta may be rich in lanthanides, a group of heavy elements that strongly block blue light. Other ejecta may contain fewer of them and allow bluer emission to escape earlier. The observed color evolution therefore points backward into the collision, revealing not a simple expanding cloud but a structured outflow shaped by gravity, pressure, neutrinos, and nuclear reactions. The telescopes do not see the collision surface directly, they see the consequences arranged in time. This is why the event becomes more than a confirmation of a theory. It provides a working example of how a neutron-star merger can be studied across many scales at once. The motion of the compact stars is measured by gravitational waves. The high-energy flash constrains the launch of a jet or fast outflow. The kilonova glow traces the bulk of the expanding debris. The host galaxy places the event in an astrophysical setting. Together, these observations allow astronomers to test a chain of ideas that had previously been supported in fragments. Short gamma-ray bursts, neutron star mergers, kilonovas, and heavy element production had all been linked by theory and by indirect evidence. In this one event, the links become visible in sequence. Not every detail is settled, and the data does not remove all uncertainty. The exact structure of the jet, the mass of the remnant, and the detailed composition of the ejecta remain subjects of study. But the broad outline is no longer speculative in the same way. A neutron star merger has been detected in gravitational waves, followed by gamma rays, then by a fading optical and infrared source in a nearby galaxy. The sky has answered in several languages at once, and the combined answer is more precise than any single observation could have been. By the end of the first observing campaign, the event is no longer just a point of light near NGC 4993 or a waveform in LIGO data. It has become a connected physical record, from inward spiral to outward debris. The next question is what that debris is, and why its changing colours reveal the quiet manufacture of some of the heaviest matter found on Earth. A neutron star begins as the remaining core of a massive star after the outer layers have been thrown into space. During the earlier life of the star, gravity and internal pressure hold each other in a long balance. Nuclear fusion in the core releases energy, and that energy helps support the star against its own weight. When the usable fuel in the center is exhausted, the balance fails. The core can no longer resist collapse in the same way, and under the right conditions, the inward fall becomes extreme. Electrons and protons are pressed together, forming neutrons and releasing neutrinos. The outer layers are driven outward in a supernova, while the core is left behind as an object with more mass than the Sun packed into a sphere only about the size of a city. This is the origin of the neutron star as a physical object, not a normal star shining by fusion, but a compact remnant supported by the behaviour of matter under enormous pressure. Its density is difficult to compare with anything familiar because the comparison quickly becomes misleading. The important point is that the matter is compressed to nuclear scales. Inside atoms on Earth, most of the volume is empty space around a tiny nucleus. In a neutron star, that ordinary structure is no longer preserved in the same way. Matter has been forced into a condition where atomic boundaries are gone, and the rules are governed by dense nuclear matter, quantum pressure, and gravity acting together. The surface may have a crust made of nuclei and electrons, but deeper layers become stranger and less certain. Physicists can model these interiors, but they cannot reproduce the full conditions in a laboratory. This makes neutron stars valuable not only as astronomical bodies, but as natural tests of matter at its limit. Their masses can be measured in binary systems. Their radii can be estimated from X-ray observations and gravitational wave signals. Their behavior can reveal how dense matter resists further collapse. Yet even with modern data, the exact equation of state, the relationship between pressure, density, and composition inside the star, remains one of the central open questions. A neutron star is therefore both known and partly hidden. Its existence is well established. Its broad origin is understood. Its deepest interior still lies beyond direct reach. When two neutron stars form a binary system, their later fate depends on the orbit left behind after the deaths of the original stars. The system may begin as two massive stars born together. Each evolves, collapses, and leaves a compact remnant. If the binary survives the explosions and any kicks produced by the supernova, the result can be two neutron stars circling a common center of mass. At first, the separation may be wide enough that the system appears stable over human timescales. Nothing about the orbit looks like an immediate collision. But general relativity changes the long-term account. A pair of massive compact objects in orbit emits gravitational waves, carrying energy away from the system. As energy leaves, the orbit shrinks. The stars move closer together. As they move closer, they orbit faster, and as they orbit faster, they emit gravitational waves more strongly. The process feeds on itself slowly at first, then rapidly near the end. A binary that may have taken millions or billions of years to decay can finish its last stage in a brief and measurable sweep. This is the motion recorded by LIGO in the August event. The signal is not produced by an explosion in the ordinary sense. It is produced by the changing gravitational field of two dense objects accelerating around each other. The frequency rises because the orbit is tightening. The amplitude grows because the motion is becoming more intense. The final approach is unavoidable once the system reaches this stage because there is no mechanism left to restore the lost orbital energy. The stars are no longer simply companions. They are remnants moving toward contact under the consequences of gravity itself. As the separation decreases, the surfaces and interiors of the neutron stars begin to matter more directly. If the objects were perfect point masses, their motion would be simpler to describe. Real neutron stars can be distorted by tidal forces. Each star pulls more strongly on the near side of the other than on the far side, stretching it slightly. The degree of stretching depends on the size and stiffness of the star. This effect is small compared with the overall gravitational motion, but it carries information. A larger or more easily deformed neutron star leaves a different imprint on the late-in spiral than a smaller, more compact one. This is why the gravitational wave signal can place limits on neutron star structure. The merger is not only a collision of masses, it is an encounter between two bodies made of dense matter with finite size. Near the end, the orbital speed becomes a significant fraction of the speed of light. The stars circle each other many times each second. Their outer layers may begin to deform strongly, and material can be squeezed, heated, and pulled into streams. The exact sequence depends on the masses of the stars, their spins, their internal structure, and how the final remnant forms. In some cases, a massive neutron star may survive briefly after the merger before collapsing. In others, the collapse to a black hole may be almost immediate. Between these outcomes lies a short and complex interval where gravity, nuclear physics, neutrino emission, magnetic fields, and fluid motion all influence the matter around the center. That interval is difficult to observe directly, but its consequences appear in the debris. Some material is thrown outward during the final collision. Some remains in a hot disk around the central remnant. Some falls inward. The balance among these channels shapes the kilonova that follows. The reason neutron star mergers are especially important for kilonovas is the nature of the material they eject. Ordinary stellar explosions can release many elements into space, but the heaviest elements require conditions with large numbers of free neutrons. Neutron star matter provides such a setting because the stars are built from neutron-rich material. When pieces of this matter are expelled and expand into space, they move away from the extreme pressure that kept them in a dense state. The material decompresses, temperatures and densities change quickly, atomic nuclei form and capture neutrons, radioactive nuclei decay, heating the expanding debris and powering the glow, observed as the kilonova. This connection between compact star physics and visible light is what makes the merger so scientifically rich. The gravitational wave reveals the bodies before they merge. The later light reveals what happens to matter after it escapes. A neutron-star collision is therefore not only a final orbit, it is a transition from hidden density to observable chemistry. The dead stars meet under conditions where their earlier histories, their internal structure, and their orbital decay all become part of one event. The original massive stars may have lived and died long before the merger, leaving behind remnants that circled quietly through their host galaxy. For most of that time, the system would not have looked explosive. The loss of energy to gravitational waves would have been steady but small. Only near the end would the process accelerate into the range detectable from Earth. By the time LEGO records the final in spiral, the long preparation is almost complete. The stars have crossed from slow orbital decay into rapid merger. Their matter can no longer remain contained in two separate bodies. The collision begins as a prediction of relativity and ends as an astrophysical source of light, heat, and new nuclei. This is why the section of the story centered on the stars themselves is essential. The later colors, spectra, and heavy elements do not arise from an unspecified explosion. They arise from the specific nature of neutron stars' compact remnants, with nuclear density interiors, strong gravity, and matter rich in neutrons. Their merger produces gravitational waves because dense masses accelerate in a shrinking orbit. It produces a kilonova because some of their matter is expelled and transformed as it expands. The two parts cannot be separated. Without the long-in spiral, there is no collision. Without the dense material, there is no neutron-rich debris. Without the ejected debris, there is no kilonova glow to reveal the chemical aftermath. The dead stars meet only after a long loss of orbital energy, but when they do, the encounter opens a short-lived window into physics that is normally buried inside the smallest and densest stars known. The kilonova appears only after the central collision has already passed beyond direct view. The neutron stars have spiraled inward, their surfaces have met, and the densest material has either collapsed toward a central remnant or been driven into violent motion around it. What becomes visible from Earth is not the point of contact itself, but the expanding matter that escapes. This debris carries the physical memory of the merger. It moves outward at a substantial fraction of the speed of light, hot, dense, and rich in free neutrons. As it expands, it becomes a temporary source of light, powered not mainly by a shockwave moving through a large star, and not by hydrogen fusion, but by radioactive decay inside freshly assembled nuclei. That is the defining feature of a kilonova. It is a short-lived glow created when neutron-rich material from a compact merger changes its nuclear identity while spreading into space. The word can make the event sound like a simple scale between a nova and a supernova, but its origin is different from both. A classical nova occurs on the surface of a white dwarf that draws gas from a companion star. A supernova usually marks the catastrophic death of a massive star, or the thermonuclear disruption of a white dwarf. A kilonova comes from compact remnants that have already died once as ordinary stars. Their explosion is not the first stellar death, but the delayed consequence of two dead cores finally meeting. This difference matters because it changes the source of the light. In a supernova, a large stellar envelope can remain bright for weeks or months as heat, radioactive material, and expanding gas interact across an enormous volume. In a kilonova, the ejected mass is much smaller, but it moves quickly and contains nuclei that are highly unstable. The glow rises and fades faster. Its temperature and colour evolve over a short time because the debris is expanding rapidly, and because its opacity, the ability of matter to block light, is shaped by the heavy elements forming within it. The event near NGC 4993 shows this behaviour clearly enough to separate it from more familiar transients. It is bright, but it is not bright in the same way as a supernova. It is brief, but it is not just the fading afterglow of a gamma-ray burst. It occupies its own category, and that category is tied directly to the physics of neutron-rich ejecta. The first important step is the ejection itself. During the merger, some material can be flung outward by tidal forces as the stars deform and pull on each other. Other material can be pushed out by shocks when dense surfaces collide. Still more may leave later in winds from a hot disk of matter around the central object. These channels are not identical. They can have different speeds, different directions, and different neutron content. This means the kilonova is not produced by a perfectly uniform shell. It is more likely a layered and uneven outflow, with some material relatively poor in the heaviest R-process products, and other material rich in them. The observed glow is the combined result of these components, each cooling and radiating in its own way. The early light may come from faster or less opaque ejecta, while later emission can be dominated by material that blocks blue light more strongly and releases energy at longer wavelengths. Even before the details of composition are examined, the overall behaviour tells astronomers that the debris is unusual. It fades too quickly for a normal supernova and carries the imprint of matter that ordinary stellar explosions do not easily provide. The energy source is also distinctive. When free neutrons are captured by atomic nuclei in the expanding debris, many of the resulting nuclei are unstable. They decay toward more stable forms, releasing energy. Some of that energy is absorbed by the surrounding material and then re-emitted as light. This radioactive heating is what keeps the kilonova visible after the initial violence of the collision. The brightness depends on how much material is ejected, how fast it expands, and how efficiently decay energy is converted into radiation. The mass involved can be only a small fraction of the Sun, yet that is still enough to create a luminous event visible across 130 million light-years. The material does not need to rival a supernova in total mass because the nuclear processes inside it are so energetic, and because the event is observed with sensitive instruments prepared to follow it quickly. The short timescale is part of the evidence. As the debris expands, its density falls. Photons escape more easily from some layers, while other layers remain difficult to see through, because heavy elements produce dense forests of absorption lines. The light curve, which records brightness over time, therefore becomes a diagnostic tool. It shows how the event releases stored nuclear energy as the ejecta thins and cools. In the August event, the fading source near NGC 4993 behaves in a way that matches kilonova predictions developed before the observation. That match is not perfect in every detail, and it does not remove the need for improved models, but it confirms the broad physical picture. A neutron-star merger can eject matter. That matter can undergo rapid neutron capture. The decay of newly formed nuclei can power a transient glow. The result can be found by telescopes when gravitational waves and gamma rays provide the warning. This sequence gives the kilonova its scientific importance. It is not an isolated flash with an unknown cause. It is the visible surface of a deeper chain that begins in orbital decay and ends in nuclear transformation. The distinction from a gamma-ray burst afterglow is especially important. A gamma-ray burst afterglow comes from fast outflow interacting with surrounding material, producing emission across wavelengths as particles are accelerated. A Kilonova glow comes from the expanding merger debris itself, heated internally by radioactive decay. In the same event, both can exist. The challenge is to separate them by timing, color, spectrum, and behavior. In the first days after GW 170817, the optical and infrared emission is too bright and evolves too quickly to be explained as a simple afterglow alone. It points to an additional source of power, one located in the radioactive material thrown out by the merger. Later, X-ray and radio signals help trace the jet and its interaction with the environment. But the early optical and infrared light belongs to the kilonova. This layered interpretation prevents the event from being reduced to one emission process. The collision produces several physical outcomes at once, and each becomes visible under different conditions. There is the gravitational wave from the in-spiral. There is the short high-energy burst. There is the radioactive glow from ejector. There is later emission from outflows meeting surrounding gas. The kilonova occupies the central place in the chemical story because it contains the material that escapes the merger with enough neutrons to build heavy nuclei. The expansion of that material is also what gives the event its calm but profound importance. It shows that a process hidden in extreme density can become observable once matter is released from the gravitational center. Inside a neutron star, the conditions are too compact and opaque to expose ordinary clues. Outside, in the cooling debris, nuclear reactions leave marks in light. The kilonova is therefore a translation from inaccessible matter to measurable radiation. It does not show individual atoms being built one by one, but it shows the collective behavior expected when many unstable heavy nuclei form and decay together. Its brightness, timescale, and spectrum all point back toward the same source. The material has been expelled from neutron stars and is changing as it expands. The appearance of the kilonova also clarifies why the event could not have been understood by light alone without the gravitational trigger. A fast-fading optical transient in a distant galaxy might have been noticed, but its full meaning would have been harder to establish. It could have been compared with unusual supernovae or other transient classes. The gravitational wave identifies the compact merger at the start. The gamma rays connect the event to high-energy outflow. The optical and infrared glow then reveals the ejector. Together, the signals make the interpretation stable. The kilonova is not merely a name given to a fading point of light. It is the expected visible consequence of neutron-rich matter escaping a neutron-star merger. In that consequence, the universe provides a rare view of matter, moving from one extreme state into another, from the crushed interior of dead stars into expanding debris where nuclear decay can be observed across intergalactic distance. The glow is temporary, and within a short time it fades beyond easy reach. But while it lasts, it carries information that no static object could provide. It shows that the collision did not only merge two remnants, it released matter, changed that matter, and allowed the change to be measured. The next layer of the evidence lies in how the light shifts as the debris cools, because the colours of the kilonova are not decorative features. They are the first visible signs of what the escaping material has become. The first colour of the kilonova is not the colour that lasts. In the early observations near NGC 4993, the source appears relatively blue, meaning that much of its escaping light is concentrated at shorter visible wavelengths. This early blue emission tells astronomers that at least some of the debris is hot, expanding rapidly, and not yet so opaque that shorter wavelengths are trapped. But the blue phase fades quickly. Within a short span, the light shifts toward redder wavelengths, and infrared emission becomes increasingly important. This change is one of the most important clues in the entire event, because colour in astronomy is not only a visual description, it is a measurement of temperature, opacity, composition, and motion. A hotter source tends to emit more strongly at shorter wavelengths. A cooler source emits more strongly at longer wavelengths. But in a kilonova, temperature alone is not enough to explain what happens. The matter itself changes the path that light can take. As the debris expands and heavy nuclei form, some elements absorb and scatter light so efficiently that they reshape the glow from within. The observed transition from blue to red therefore becomes evidence that the ejector is not chemically simple. It is becoming filled with newly assembled heavy matter, and that matter changes how radiation escapes. This is why the colour evolution of the kilonova drew such close attention. The event was not merely fading, it was fading in a way that carried information about the elements inside it. The first blue component likely comes from material with relatively lower opacity, meaning light can pass through it more easily. This material may have been influenced by neutrinos from the hot merger remnant or from the disk around it. Neutrinos are light, nearly invisible particles that can carry energy away from dense astrophysical environments and, under certain conditions, change the balance of neutrons and protons in the escaping matter. If some ejector has fewer free neutrons relative to protons, it may form fewer of the heaviest lanthanide elements. Lanthanides are a group of heavy elements whose electron structures make them especially effective at blocking blue and visible light. When they are less abundant, the debris can glow more blue at first. That early light is therefore not a simple surface colour. It points to a particular kind of ejector, one that may have escaped through polar directions or from wind-like outflows, where the composition was altered before the heaviest elements fully dominated. The later red and infrared light points to a different component. This material is richer in neutrons and more favourable for forming lanthanides and other heavy nuclei. Its opacity is much higher, so blue light is absorbed and reprocessed. Radiation takes longer to escape and emerges at longer wavelengths. The same explosion therefore reveals at least two kinds of material, not separated by a sharp wall, but by composition, direction, speed, and origin in the merger. A kilonova is often described as a single event, yet its colours show that the outflow is structured. Some matter may be squeezed out during the first contact of the neutron stars. Some may be pulled into tidal tails by gravity. Some may be blown from the hot disk left around the remnant. Each path can leave a different chemical signature. The observed light is the combined result of these routes, and the colour shift is the way that structure becomes visible. Spectroscopy adds another layer, although it is difficult in this case. In many astronomical objects, spectra can identify elements through sharp lines, because atoms and ions absorb or emit light at specific wavelengths. In kilonova debris, the situation is more crowded. Heavy elements, especially lanthanides, have complex electron arrangements that produce vast numbers of overlapping features. Instead of clean, narrow fingerprints, the spectrum can become broad and blended, shaped by rapid expansion, as well as by many possible elements at once. This makes precise identification harder. Astronomers cannot simply point to one clean line and declare that a particular element is present in a simple way. The evidence is more indirect. The overall colour, brightness, fading rate, and broad spectral shape are compared with models of expanding radioactive debris. Those models show that lanthanide-rich ejecta should look redder and remain bright in infrared wavelengths longer than lanthanide-poor material. The kilonova follows that broad expectation. Its light first contains a bluer component, then becomes dominated by redder emission. This does not mean every atom inside the debris is individually known. It means the physical behavior matches the presence of heavy element-rich material in a way that ordinary alternatives do not easily reproduce. The color change also reveals the speed of the event. The debris expands so quickly that its density falls from hour to hour and day to day. As density drops, photons find changing routes through the material. At the same time, radioactive decay continues to heat the gas from within. The brightness observed from Earth depends on a balance between heating, expansion, cooling, and opacity. If the debris expands too quickly, it thins and fades. If radioactive heating remains strong, it continues to glow. If opacity is high, energy escapes later and at longer wavelengths. These competing effects turn the light curve into a record of physical conditions. The blue light declines quickly because the hot, less opaque component cools and expands. The redder component persists somewhat longer because heavy elements delay the escape of radiation and shift it into the infrared. That sequence is not decorative. It is a sign that nuclear reactions and radiative transfer are working together. Radiative transfer is the movement of radiation through matter, and in a kilonova it becomes inseparable from composition. The same radioactive nuclei that heat the ejecta also help determine how the light is filtered before it reaches space. The observation is especially powerful because the color shift had been predicted before the event. Models of neutron star mergers suggested that material with different neutron richness would produce different kilonova components. A lanthanide-poor outflow could produce an early blue glow. A lanthanide-rich outflow could produce a later red and infrared glow. The August event gave astronomers a real source in which that pattern could be tested. The match did not make every model exact, but it showed that the basic framework was sound. It also made clear that observations across many wavelengths are necessary. An optical telescope alone might follow the early fading but miss much of the later infrared emission. An infrared telescope alone might see the red component but lose the first evidence of hotter, less opaque ejecta. The full story requires the transition. The kilonova has to be watched as it changes, because the change is the evidence. In this sense, the event is more like a timed experiment than a static object. The first night, the next day, and the following observations each record a different layer of the same expanding matter. The color evolution also helps separate the kilonova from other cosmic transients. Supernovae can change color as they cool, but their timescales and energy sources are different. They often involve much larger masses of ejecta and remain bright for longer periods. Ordinary afterglows from gamma-ray bursts can also fade and shift, but they are powered by external shocks rather than by radioactive decay in heavy element-rich material. The kilonova near NGC 4993 fades quickly, reddens rapidly, and carries the expected signature of neutron-rich debris. Its behavior fits the merger interpretation already supplied by gravitational waves. That agreement between independent clues is what gives the color data its strength. The gravitational signal identifies the source as a compact merger. The gamma rays show prompt high-energy emission. The optical and infrared colors show the nature of the expanding debris. Each piece limits the possible explanations for the others. The color does not stand alone, but it becomes decisive because it belongs to the right event at the right time. Behind the changing light lies the larger problem of how matter behaves when it is released from neutron star density. Inside the stars, Matter is locked under extraordinary pressure. Once expelled, it expands so fast that nuclear reactions occur in a moving, cooling environment. Nuclei form, capture neutrons, decay, and heat the surrounding gas. The products are not distributed in a calm laboratory sequence. They emerge in debris racing away from one of the densest collisions in nature. The light that reaches Earth is therefore a softened final signal from a very complex process. It has passed through material that is itself still changing. When the kilonova turns red, astronomers are not seeing a surface painted by one element. They are seeing radiation filtered through a new mixture of heavy nuclei, many unstable, many difficult to identify individually, all affecting the escape of light. That is why the redwood shift matters so deeply. It shows that the merger has moved beyond energy release into element formation. The glow is no longer only evidence that matter was ejected. It is evidence that the matter has been transformed. As the kilonova fades into infrared and then into darkness, it leaves behind a clearer interpretation than brightness alone could provide. The debris is fast. It is hot at first, then cooling. It is neutron-rich in at least part of its mass. It contains heavy elements that strongly reshape the escaping light. The color record turns the event from a detected explosion into a chemical environment. From that point, the next question becomes more exact. If the shifting light reveals heavy matter, then the process that built that matter must be followed into the nuclei themselves, where rapid neutron capture can assemble elements beyond the reach of ordinary stellar fusion. Rapid neutron capture begins with a simple requirement and then becomes difficult very quickly. To build atomic nuclei heavier than iron, nature needs more than heat. It needs a place where neutrons are abundant enough to enter nuclei before those nuclei have time to settle into more stable forms. In ordinary stars, fusion can build elements by joining lighter nuclei together, but fusion becomes less effective as nuclei grow heavier. Iron and nearby elements sit near a deep point of nuclear stability, where further fusion no longer releases useful energy in the same way. To pass beyond that region, another path is needed. One path is slow neutron capture, in which a nucleus absorbs a neutron and often waits long enough for radioactive decay to change one of its neutrons into a proton before the next neutron arrives. That process can build many heavy elements over long periods inside certain stars, but it cannot easily account for all of the heaviest nuclei, especially when the pattern of abundances in the universe points to a faster route. Rapid neutron capture is that faster route. It requires an environment so rich in free neutrons that nuclei absorb them again and again before radioactive decay can catch up. The result is a temporary movement into very neutron-heavy versions of atoms, far from the stable nuclei normally found on Earth. These unstable nuclei do not remain in that form. After the neutron supply falls away, they decay back towards stability, and as they do, they become heavier elements with more protons than they had at the start. This is the basic logic behind the process. A flood of neutrons pushes nuclei outward into unstable territory. Then decay reshapes them into heavy elements that can survive. A neutron-star merger provides a natural setting because the material involved is already rich in neutrons. The stars themselves are made from matter compressed into an extreme state. And when some of that matter escapes the collision, it decompresses into conditions unlike the interior that held it. The pressure drops, the temperature changes. Free neutrons become available on a large scale. Atomic nuclei can form and begin capturing neutrons at a speed that ordinary stellar environments cannot match. This is why the merger is so important for the origin of heavy elements. It is not only energetic. Energy alone is not enough. A supernova can be extremely powerful, but if the right neutron-rich conditions are not maintained, it may fail to produce the needed amount of the heaviest elements. The neutron star merger brings both violence and composition together. It throws out matter that is not simply hot gas, but material with the right nuclear ingredients. The capture process happens in expanding debris, not inside a calm star. That expansion is crucial because the material is changing while the reactions occur. At first, densities and temperatures may be high enough for nuclei and free particles to interact rapidly. As the debris moves outward, the density falls, and the opportunity for neutron capture gradually ends. The nuclear pattern that remains depends on how many neutrons were available, how fast the material expanded, how hot it became, and how much the composition was altered by neutrinos from the central remnant and surrounding disk. These details determine whether the debris forms lighter, heavy elements, lanthanides, actinides, or a mixture across a wide range. Lanthanides are important for the observed colour because they strongly block shorter wavelengths of light. Actinides include some of the very heavy radioactive elements. The process does not build only one precious metal. It can produce a broad family of heavy nuclei, some stable, some unstable, and many formed in proportions that depend on the precise conditions of the outflow. The phrase rapid neutron capture can sound like a single step, but it is really a chain of many nuclear events happening in a short and changing environment. A seed nucleus captures a neutron, then it captures another and another, moving into increasingly neutron-rich forms. Some nuclei may become so heavy that they split apart through fission, sending pieces back into the reaction flow and allowing further captures to occur. This recycling can shape the final abundance pattern, especially among the heaviest nuclei. Meanwhile, radioactive decays begin to compete as the neutron supply thins. The path that matter follows through the chart of nuclei is therefore not fixed by one reaction. It is guided by a balance among capture, decay, fission, heating, and expansion. The final mixture is a record of that balance. This is why scientists use computer models to compare the observed kilonova light with possible nuclear outcomes. Directly observing each reaction is impossible at a distance of roughly 130 million light-years. Instead, the models connect nuclear physics to visible and infrared behavior. If the debris contains many lanthanides, the light should become redder and remain important in the infrared. If it contains fewer, the early blue component should be easier to see. If the total ejected mass is larger, the glow may be brighter and last longer. If the material expands faster, the light may peak and fade sooner. The kilonova therefore becomes a way to infer nuclear processes through their collective effect on radiation. It is an indirect method, but not a weak one. The same event supplies gravitational waves, gamma rays, optical light, and infrared light, and each piece limits the range of acceptable models. The evidence from the colour shift does not prove the exact inventory of every element, but it strongly supports the formation of heavy material in the ejector. This matters because the origin of the heaviest elements had remained unsettled for a long time. The universe contains gold, platinum, uranium, and many related nuclei, yet their formation requires conditions that are not common in ordinary stellar burning. The rapid neutron capture process was understood in principle before neutron star mergers were directly observed, but the astrophysical site was debated. Some supernovae may contribute under certain conditions, and the full story of heavy element production may involve more than one source. But the kilonova connected to GW 170817 showed that neutron star mergers can produce the right kind of debris in the right kind of event. The observed glow matched what was expected from radioactive heating by heavy nuclei. Its rapid reddening matched the effect of high-opacity material. Its association with a confirmed neutron star merger removed much of the ambiguity that had surrounded isolated transients. The process inferred from the light is part of the power source of the glow itself. As unstable nuclei decay, they release energy that heats the ejector. That heat escapes as light. The same newly formed nuclei that help explain the elements also help make the kilonova visible. This creates a close connection between origin and observation. The event shines because heavy nuclei are being formed and decaying. The light reveals the process because the process powers the light. The scientific strength of the observation lies in that coupling. The merger does not merely scatter pre-existing material, it creates new nuclear products while producing a signal that can be measured from Earth. Still, caution remains important. A Kilonova spectrum is complex, and the abundance of a single element such as gold cannot be read from one clean line in the data. Estimates of how much gold or platinum was made depend on models of the ejector mass, composition, and nuclear reaction networks. These estimates can be large, but the exact amounts are not directly weighed. What is secure is the broader conclusion. The event produced a substantial quantity of neutron-rich ejecta, whose light is consistent with heavy element formation through rapid neutron capture. That conclusion is already powerful without pretending to know every detail. It places neutron star mergers among the central factories of the heavy elements. The atoms formed in such events do not remain forever near the merger site. Over long periods, debris from many explosions and collisions mixes into interstellar gas. Later generations of stars and planets form from that enriched material. Some atoms on Earth, including atoms in precious metals and radioactive minerals, may owe their existence to events of this kind in the history of the galaxy. The August kilonova does not identify the exact source of any particular atom on Earth, but it demonstrates a working mechanism by which the universe can produce such atoms. The movement from neutron star matter to expanding debris to heavy nuclei closes a gap that ordinary stellar fusion could not close by itself. Rapid neutron capture is therefore the inner engine of the kilonova's chemical meaning. It explains why neutron-rich matter is so valuable to the cosmic inventory, why the color of the event changes, and why a merger of dead stars can seed space with elements that later become part of planets. The process remains difficult to model in full, because it depends on nuclear data for unstable isotopes that are hard or impossible to study directly on Earth. It also depends on the uncertain structure of neutron stars and on the behavior of the merger remnant, but the outline is now anchored by observation. A confirmed neutron star collision produced a fading glow whose properties match heavy element formation. The next question follows naturally from that evidence. If rapid neutron capture can build the heaviest nuclei in kilonova debris, then the precious and rare elements found in planets are not separate from the violence of compact stars. They are one of its long-delayed consequences. Gold is rare on Earth because it is difficult for nature to make. Its atoms are heavy, with nuclei that contain many protons and neutrons, and ordinary stellar burning does not build them in a straightforward way. The same is true for platinum, uranium, and many other heavy elements that appear only in small amounts in rocks, meteorites, and stars. Their rarity is not only a matter of chemistry, it is a record of nuclear history. To understand why a ring, a catalyst, a grain of ore, or a radioactive mineral contains these atoms at all, the story has to move beyond the stable life of stars and into brief environments where nuclei are driven far from ordinary conditions. For a long time, supernovae were the main candidates. They were the most obvious large explosions known in the universe, and they clearly returned many elements to space. Massive stars make oxygen, silicon, sulfur, calcium, iron, and related elements through successive stages of fusion and collapse. Their deaths scatter this material into the interstellar medium, enriching later generations of stars and planets. It was reasonable to look there for the heaviest nuclei as well. Yet the more carefully the problem was modelled, the more difficult it became to make every part of the heavy element inventory with ordinary supernova conditions. The obstacle was not a lack of energy. It was the need for an intense supply of neutrons under the right timing, density, and expansion. Some supernova models can produce neutron-rich regions, and they may still contribute in special cases, but the full pattern of heavy elements required another source, or at least a source that had not been directly confirmed. Neutron star mergers offered that source because they begin with matter already rich in neutrons. The idea had a strong physical basis before the august detection, but it lacked the decisive observational chain. The universe contained heavy elements. Nuclear physics described a rapid path for building them. Neutron star collisions seemed capable of providing the needed material. What was missing was a witnessed merger whose light behaved as if heavy nuclei had actually formed. The Kilonova supplied that missing link. It did not show a single gold atom being made, and it did not produce a simple chemical label attached to one spectral line. Instead, it gave a broader and more reliable signature fast ejector, radioactive heating, rapid fading, a shift from blue to red and infrared, and a confirmed origin in the collision of neutron stars. Those features together made the event a working example of heavy element production in the universe. The importance of gold and platinum in this story is partly cultural, because they are familiar and valued, but scientifically they are examples of a much larger group. Heavy elements beyond iron include many nuclei that shape planetary interiors, radioactive heating, geologic timekeeping, industrial technology, and the chemistry of rare materials. Uranium and thorium help provide long-term heat inside rocky planets through radioactive decay. Certain rare earth elements influence magnetic materials and electronics. Platinum group elements have unusual chemical properties useful in catalysts. These atoms are not abundant, but their effects can be significant. Their existence shows that the chemical inventory of a planet is not made only by calm stellar burning. It also carries contributions from rare, violent events that occurred before the planet formed. The Kilonova therefore connects extreme astrophysics with the ordinary material world. Not by suggesting that a particular nearby collision supplied Earth directly, but by showing how such collisions can enrich the gas from which later systems are born. Over long timescales, the debris from mergers spreads into surrounding space. It mixes with material from stellar winds, supernovae, and other sources. New stars then form from clouds that already contain the products of many earlier generations. The solar system inherited such a mixture. Its heavy elements are a fossil record of events that happened before the Sun existed. Some of that record likely includes neutron star mergers, though the exact contribution from each kind of source remains an active question. One of the difficulties is timing. Neutron star mergers can occur long after the stars that created them first formed. Because binary systems may take millions or billions of years to spiral together, if mergers were too delayed or too rare, they might struggle to explain heavy elements found in very old stars that formed early in the history of the galaxy. Observations of ancient stars show that some heavy elements were present surprisingly early. This does not rule out neutron star mergers, but it requires careful modelling of how often they happen, how quickly some binaries merge, how far their ejector travels, and how efficiently their material mixes into star-forming gas. Some systems may merge quickly after formation. Others may take much longer. Some may be kicked away from their birthplaces by earlier supernova explosions, releasing their debris in less dense regions where mixing proceeds differently. The Kilonova confirms that mergers can produce heavy elements, but it does not by itself prove that they are the only source. A calm scientific answer has to keep both facts in place. The event is strong evidence for a major production channel, while the complete galactic accounting still has uncertainties. The yield from a single neutron-star merger can be large compared with the tiny amount of heavy elements needed to enrich a region of gas. Models of the August kilonova suggest that a significant mass of neutron-rich material was expelled, enough to include substantial quantities of heavy nuclei. Popular descriptions often emphasize possible Earth masses of gold or platinum because that comparison is vivid, but the more important point is the total heavy element production across the ejector. The merger releases a mixture, not a volt of one element. Gold, platinum, and uranium are part of a broader nuclear outcome shaped by the rapid capture of neutrons and later radioactive decay. The exact fractions depend on the electron fraction of the ejector, the entropy, the expansion rate, and the nuclear reactions among unstable isotopes. These terms describe how many protons are present compared with neutrons, how energy and disorder are distributed, how quickly the material thins, and how nuclei behave far from stability. In plain language, the final chemical mixture depends on what kind of matter escaped and how it cooled. The observation gives enough evidence to identify heavy element formation, while leaving detailed abundance estimates to models that continue to improve. This is not a weakness in the discovery. It is the normal condition of studying an event so distant and brief. Astronomers do not collect the debris directly. They infer its nature from light, motion, timing, and comparison with physical simulations. The case is strong because many independent clues point in the same direction. The gravitational wave identifies the merger. The early gamma rays show prompt high-energy activity. The optical and infrared glow behaves like radioactive ejector. The color evolution indicates high opacity associated with heavy elements. The host galaxy and distance are consistent with a compact binary system that had time to evolve before merging. Together, these observations make the kilonova a turning point in the origin story of precious elements. Before it, neutron-star mergers were a compelling theory. After it, they became observed sites where the needed process occurs. The broader implication is that the material richness of planets depends on events that are both rare and cumulative. A galaxy does not need every star to make gold. It needs enough heavy element factories over enough time, with enough mixing, to seed later generations. A single merger can contribute greatly, but its contribution becomes part of a wider chemical circulation. Gas is stirred by stellar explosions, galactic motion, and star formation. Dust grains form, break apart, and reform. Elements move between stars, clouds, and planets across immense spans of time. By the time a rocky world solidifies, its ingredients have passed through many earlier environments. Some were made in ordinary stellar cores. Some were made in explosive deaths. Some may have been formed when neutron stars collided and released neutron-rich matter into space. The origin of precious elements is therefore not a separate story from the evolution of galaxies. It is one part of how galaxies become chemically complex. The August kilonova made this connection measurable. It showed that a collision of dead stars can produce the conditions needed for the heaviest nuclei, and that the evidence can be read in the fading colours of a transient glow. The gold in a planet is not explained by brightness alone, or by energy alone, but by a specific kind of nuclear environment. Neutron-star mergers provide such an environment with unusual efficiency. They bring together compressed remnants, eject neutron-rich matter, power a radioactive glow, and distribute newly formed nuclei into space. What remains uncertain is the total share they contribute compared with other possible sources, especially in the earliest galaxies and in unusual stellar explosions. That uncertainty does not weaken the central lesson of the kilonova. It places the lesson in a larger account still being refined. The event near NGC 4993 showed that precious elements can be born from the final meeting of neutron stars. It changed the question from whether mergers can make them to how often they do, how far their material travels, and how much of the heavy matter in planets owes its existence to those compact collisions. The moment after contact is one of the least visible parts of the neutron-star merger, yet it may be the part that decides how the rest of the event unfolds. Before the collision, the gravitational wave signal can be followed through the final inspiral with relatively clear models. After the stars touch, the system changes too quickly and becomes too dense for a simple picture. Matter is squeezed, heated, torn, and driven into rotation around a central remnant whose identity may not be settled immediately. The remnant can follow several possible paths. It may collapse into a black hole almost at once. It may become a short-lived massive neutron star, held up for a brief time by rapid rotation and heat. It may survive longer as a highly unstable object before eventually collapsing. Each outcome leaves a different imprint on the matter around it, on the neutrinos that escape, on the magnetic fields that grow, and on the ejector that later powers the kilonova. This is why the central remnant matters even though telescopes do not see it directly. It is the hidden engine between the gravitational wave and the visible glow, shaping the conditions under which material is expelled and heavy elements are formed. The difficulty begins with mass. A neutron star can exist only up to a certain limit, and that limit depends on the equation of state of dense matter. If matter inside neutron stars is stiff, meaning it produces strong pressure as density rises, a heavier neutron star can resist collapse. If it is softer, collapse happens at a lower mass. The merger brings together two neutron stars whose combined mass is greater than either one alone. Some mass escapes as debris. Some energy is radiated away in gravitational waves and neutrinos, but much of the system remains in the center, where gravity presses toward collapse. Whether the remnant becomes a black hole quickly or temporarily remains a neutron star depends on this balance. The august event therefore becomes a test of matter at densities beyond atomic nuclei. The remnant is not only an object in space, it is a question about how pressure behaves when matter is compressed as far as nature allows before an event horizon forms. A prompt collapse would produce a black hole surrounded by a disk of hot material. In that case, the central object has no surface, and matter outside it either falls in, escapes, or remains in orbit for a short time. A longer-lived neutron star remnant would be different. It would have a surface, or at least a dense boundary, a powerful magnetic field, intense neutrino emission, and rapid rotation. These features could change the composition of the outflows. Neutrinos streaming from the remnant can convert some neutrons and protons into each other, altering the neutron richness of nearby ejecta. That change affects which heavy elements form and how opaque the debris becomes. A remnant that survives even briefly can therefore help produce a bluer early kilonova component by reducing the amount of the heaviest lanthanide-rich material in some directions. A remnant that collapses almost instantly may leave less time for such processing. The color of the kilonova is therefore indirectly connected to the lifetime of something hidden at the center. The observed early blue light in the august event suggests that at least some ejecta had relatively lower opacity. This does not prove one remnant outcome by itself, but it places pressure on the models. The central object likely didn't collapse in a way that prevented all neutrino-processed or disk-driven ejecta. At the same time, the later red and infrared emission shows that very neutron-rich material also escaped. The event contains both signs matter that behaves as if it formed fewer lanthanides and matter that behaves as if it formed many. This mixture points to a merger with more than one ejecta channel and a remnant environment complex enough to produce different compositions. The central remnant may have existed long enough to influence the surrounding matter, yet not necessarily long enough to remain stable. The absence of a long-lasting, extremely bright energy injection in the observed light also argues against a remnant that survived indefinitely as a powerful magnet air. A magnetar is a neutron star with an especially strong magnetic field, and a stable magnetar formed in the merger could have poured additional energy into the ejector. The Kilonova was bright, but not in a way that required such a long-lived engine. This places the remnant in a narrow and interesting category. It may have been massive, hot, rapidly rotating, and temporary, a body supported for a short time by conditions that could not last. The transition from remnant to black hole, if it occurred after a delay, would be hidden from direct sight but not without consequence. During that interval, the remnant and disk could launch winds, magnetic fields could be amplified by turbulent motion, neutrinos could escape from dense, hot matter. The disk could feed material inward while also losing some mass outward. Each of these processes helps decide how much matter becomes unbound and what composition it carries. The kilonova is therefore not only a product of the initial impact, it is also a product of the short aftermath, when the central remnant and its disk continue to process matter before it escapes. This distinction matters because the heavy element yield depends on more than the total mass of the neutron stars. It depends on the shape, speed, and neutron richness of the ejector, all of which can be changed by the central engine. The merger remnant also affects the gamma-ray burst. To produce a short gamma-ray burst, the system likely needs a compact central engine capable of launching a relativistic jet, a narrow outflow moving near the speed of light. In many models, a black hole surrounded by an accretion disk provides such an engine. In others, a short-lived neutron star remnant may play a role before collapse. The jet has to find a path through surrounding debris. If the debris is too heavy in the polar regions, it can choke or weaken the outflow. If a cleaner channel opens, gamma rays can escape. The faintness and later behavior of the August gamma-ray burst suggest that the jet may not have pointed directly at Earth, or that the outflow had structure, with a bright core and weaker material around it. Again, the remnant is hidden, but its influence appears in the geometry and timing of what escapes. The central question remains difficult because the strongest gravitational wave information came from the in-spiral, not from the turbulent merger remnant. The high-frequency signal after contact is harder to detect with current instruments, especially at the distance of the event. If future detectors become more sensitive to that stage, they may read the oscillations of the remnant directly and reveal whether it vibrates as a massive neutron star before collapse. For now, astronomers infer the outcome by combining clues: the total mass measured from gravitational waves, the amount and color of kilonova emission, the presence of a gamma-ray burst, the later X-ray and radio afterglow, and the limits imposed by nuclear physics. This kind of reasoning is careful rather than final. It builds a likely history from consequences. The remnant may have existed for milliseconds, seconds, or perhaps longer, depending on the model. But the available evidence points toward an object that did not remain permanently stable. It was probably a threshold object, briefly supported by rotation and heat before gravity won. That threshold is scientifically valuable because it lies close to the maximum mass a neutron star can bear. If the remnant collapsed too quickly, certain ejector features become harder to explain. If it survived too long, the light might have been altered in ways not observed. The event therefore helps constrain the possible stiffness of dense matter, even without exposing the remnant directly. This is one of the quiet strengths of multi-messenger astronomy. A hidden object can be studied through the behavior of everything it affects. The remnant's lifetime changes neutrino exposure. Neutrino exposure changes composition. Composition changes opacity. Opacity changes color. Color changes the interpretation of the kilonova. A chain that begins at the densest center ends in light measured by telescopes. The aftermath of the merger is thus not a blank interval between collision and glow. It is the phase where the system chooses, under the pressure of extreme gravity. Whether to become a black hole immediately or to pass briefly through one last neutron star state, the answer controls how matter escapes and what that matter becomes. The August kilonova shows that the remnant's influence was real, even if its form remains partly uncertain. It left no direct image, and it may have existed for less time than a human breath, but the expanding debris still carries the effect of its brief presence. In that debris, dense matter, rotation, neutrinos, and magnetic fields leave indirect signatures that can be followed outward into colour, brightness, and heavy element production. The central remnant therefore remains the hidden hinge of the event, joining the inward collapse of two dead stars to the outward chemical enrichment of space. A new kind of astronomy does not begin with one instrument replacing another. It begins when different instruments stop telling separate stories and start describing the same event from different sides. The neutron-star merger near NG C4993 becomes important for this reason. It is not only a gravitational wave detection, and it is not only a burst of gamma rays, and it is not only a fading glow in visible and infrared light. It is the first event in which those channels are joined into a single physical sequence, with enough detail to follow the system from the last inward spiral to the outward movement of debris. Gravitational waves reveal the motion of the compact stars before they touch. Gamma rays show that an energetic outflow escapes soon after merger. Optical and ultraviolet observations catch the early hot glow. Infrared light records the cooler, more opaque debris where heavy elements shape the escaping radiation. Late X-ray and radio signals trace material moving into the surrounding environment. Each messenger arrives with its own limitations, but together they create a structure that is much harder to misread. This is the central change. Astronomy no longer has to ask only what kind of light reached Earth. It can ask how gravity, light, and matter describe one connected event. Before this merger, these branches of observation often work beside one another, rather than inside the same confirmed source. Gravitational wave astronomy had proved itself with black hole mergers, but those events offered little or no electromagnetic counterpart. Traditional telescopes had studied gamma-ray bursts and fast transients, but the central engines behind them could remain uncertain. The August merger joined the hidden engine to the visible aftermath. It gave astronomers a start time from gravity, a high-energy marker from gamma rays, a host galaxy, a distance, a changing source of light, and later emission from the outflow. That combination allowed the event to become more than an identification. It became a reconstruction. The order of evidence mattered. If the optical transient had been found alone, it might have been recognized as unusual, but its origin would have been less secure. If the gamma-ray burst had appeared alone, it would have joined a long catalogue of brief high-energy flashes whose engines are inferred but rarely witnessed directly. If the gravitational wave had arrived without light, it would have identified a compact merger but left the ejector, the jet, and the heavy elements mostly beyond reach. The power came from the overlap. Each signal narrowed the possible meaning of the others until a coherent picture emerged. The event also changed the scale of collaboration. No single observatory could have gathered the whole record. The detectors that measure gravitational waves are not designed to make images of fading transients. Gamma-ray satellites see high-energy flashes but cannot by themselves describe the full cooling debris. Optical telescopes can locate the source but cannot read the inspiral. Infrared instruments are needed when heavy elements push the glow toward longer wavelengths. Radio arrays and X-ray observatories become important later as the fastest outflows interact with gas around the galaxy. The discovery therefore depended on a network of tools built for different parts of the spectrum and different kinds of physics. This was not simply a large number of observers looking at the same object. It was a layered measurement, with each layer sensitive to a different stage of the merger. The result is a more complete kind of evidence. It connects an object smaller than a city to a galaxy millions of light years away, and it connects nuclear reactions inside expanding debris to ripples in the geometry of space. The event also gave astronomers a new way to measure cosmic distance. Gravitational waves can act as a kind of standard siren. The shape and strength of the signal carry information about how far away the source is, in a way that is different from the standard candles used in traditional astronomy. If the host galaxy can be identified, its motion away from Earth can be compared with the gravitational wave distance. This offers an independent route toward measuring the expansion rate of the universe. The first neutron-star merger was not precise enough to settle long-standing disagreements over that rate, but it demonstrated the method. Future events, especially with clearer signals and well-identified host galaxies, can improve the measurement. In this way, one kind of merger connects compact star physics with cosmology. The same signal that reveals two neutron stars spiraling together can also help measure how space has expanded during the signal's journey. Multi-messenger astronomy is powerful because it makes one event useful at several levels at once. It tests general relativity by comparing the arrival of gravitational waves and light across a long distance. It tests models of short gamma-ray bursts by linking them to a confirmed neutron-star merger. It tests nuclear astrophysics by showing the glow expected from rapid neutron capture. It tests dense matter through limits on neutron star size and deformability. It tests cosmic distance measurement through the relation between gravitational wave strength and host galaxy recession. None of these questions is fully answered by one observation, but the event places them in the same natural experiment. That is rare. Most astronomical objects reveal one part of physics more clearly than others. This merger carries strong gravity, high energy outflows, radioactive decay, nuclear synthesis, and galactic context together. The challenge is to keep the interpretation disciplined, because a rich event can invite overstatement. The data are extraordinary, but they still have boundaries. The gravitational wave signal is clearest before contact and less informative about the immediate remnant. The gamma-ray flash is shaped by viewing angle and jet structure. The Kilonova spectra are complex and do not provide simple labels for every element. The estimates of ejector mass and composition depend on models. The host galaxy association is secure for this event, but future mergers may be harder to localize. A new astronomy does not remove uncertainty. It changes the kind of uncertainty. Instead of wondering whether the signals belong together, scientists can ask more focused questions about how the jet was structured, how long the remnant survived, how much matter escaped through each channel, and what fraction of the heavy elements such events create across a galaxy's lifetime. The mystery becomes more precise because the evidence has firmer edges. The event also prepared the field for future detections. After the first confirmed kilonova, every new neutron star merger becomes part of a growing comparison. Some may be closer and brighter, some may be farther and barely visible. Some may produce strong gamma rays, others may produce none detectable from Earth, because the jet points away or fails to break through the debris. Some may eject more lanthanide-rich material and appear redder. Others may show stronger blue components if their remnants survive longer, or their ejector is more strongly processed by neutrinos. The diversity matters. One event proves that the mechanism exists, but a population reveals how common each outcome is. Only with many detections can astronomers determine the merger rate, the range of heavy element yields, the variety of jet structures, and the relationship between neutron star masses and kilonova brightness. The first event is therefore a beginning, not a final template. It gives the field a reference point against which later discoveries can be measured. This is a quieter kind of revolution than the word sometimes suggests. It does not replace optical astronomy. radio astronomy, X-ray astronomy, or gravitational wave astronomy. It binds them more closely. It asks each method to contribute what it can see best and to accept that no single signal is the whole event. The neutron-star merger demonstrates why that humility is useful. Gravity shows the hidden motion. Light shows the released energy. Color shows the changing matter. Delayed emission shows the outflow meeting its surroundings. The galaxy gives the event a place in cosmic history. Together, these measurements turn a distant collision into a sequence that can be followed, tested, and revised. The new astronomy begins with this kind of joining. It begins when a ripple in space and time sends telescopes toward a galaxy, when a short gamma-ray flash becomes part of a larger chain, when a fading red glow becomes evidence for nuclear creation, and when the death of two compact stars becomes a measurement of matter, gravity, and cosmic expansion at once. The next step is no longer to prove that such a combined observation is possible. That has been done. The next step is to learn what the universe looks like when these events are no longer singular breakthroughs, but members of a wider pattern waiting to be counted. The final account cannot be written from one kilonova alone. The event near NGC 4993 showed that neutron star mergers can make heavy elements and reveal them through a fading glow, but it also opened a larger problem of scale. A single confirmed event answers the question of possibility. It doesn't by itself answer the question of abundance. To know how much gold, platinum, uranium, and related nuclei come from kilonovas, astronomers need to know how often neutron stars merge, how much material each merger ejects, how different those mergers can be, and how efficiently their debris becomes mixed into the gas that later forms stars and planets. Each part of that account carries uncertainty. The rate of mergers is estimated from gravitational wave detections, from observations of neutron star binaries in the Milky Way, and from models of how massive stars live in pairs, explode, survive, and slowly spiral together. The yield of heavy elements is estimated from kilonova brightness, color, spectra, and simulations of the merger. The mixing of debris is studied through galactic chemistry and the heavy element patterns preserved in old stars. No one measurement closes the balance. The picture has to be built by combining rare events with long timescales and with evidence scattered through the chemical memory of galaxies. That is why the discovery remains active rather than complete. It gave the missing physical link, but it also made the next questions more exact. The first question is frequency. Neutron star mergers are not common in the ordinary sense. A galaxy may contain many neutron stars, but only a fraction are born in close binary systems that survive both stellar deaths and remain bound long enough to merge. Even then, the time between formation and collision can vary widely. Some systems may merge relatively quickly after the second neutron star forms. Others may orbit for billions of years before gravitational waves bring them together. This spread matters for galactic chemistry. If heavy elements appear in very ancient stars, then at least some R process sources must have operated early. Neutron star mergers can contribute if a meaningful fraction happened quickly enough, or if their ejector spreads efficiently into star-forming gas. The observed merger near NGC 4993 occurred in an older galaxy, showing that delayed mergers do happen, but the full population may include many histories. Some will occur in young environments, some in old ones, some near their birthplaces, and some far away after earlier supernova kicks moved the binary through its galaxy. Each case affects where the heavy elements are deposited. The second question is yield. The August kilonova appears to have expelled a significant amount of material, but other mergers may not eject the same amount. The masses of the two neutron stars matter. Their spins may matter, The stiffness of their interiors matters because it affects how much matter is torn away before collapse. The lifetime of the remnant matters because neutrinos and disk winds can change the composition and amount of ejecta. A prompt collapse to a black hole may leave one kind of kilonova, while a short-lived massive neutron star may produce another. Some mergers may create strong blue components, some may be mostly red and infrared, and some may be faint enough that only nearby events reveal them well. This diversity is not a complication to be removed. It is the information needed to understand the population. If every merger were forced into the pattern of the first observed kilonova, the account would become too simple. The universe is likely less uniform. The first event provides a reference, not a rule. The third question is chemical detail. Rapid neutron capture can build a wide range of heavy nuclei, but the exact mixture depends on the neutron richness, expansion rate, temperature, and nuclear reactions in the ejecta. Some material may form elements around the first R process peaks, while other material may reach lanthanides, platinum group elements, actinides, and nuclei heavy enough to undergo fission. This matters because observations of old stars show patterns, not just totals. Some stars contain strong R process enrichment, while others show different proportions. These patterns may preserve the signature of particular sources that enriched the gas from which the stars formed. Kilonovas are now known to be able to supply heavy elements, but the details of their contribution must be compared with these stellar records. The evidence from the sky and the evidence inside ancient stars are parts of the same account. One shows the process while it happens. The other shows what remains after the products have been stirred through a galaxy and locked into later generations. The fourth question is mixing. Heavy elements made in a kilonova do not instantly spread evenly through a galaxy. The ejecta moves outward, interacts with surrounding gas, cools, and eventually joins the interstellar medium. The location of the merger can influence this process. If a binary merges inside a dense star-forming region, its products may enter future stars more directly. If it merges far from the galactic disk, its debris may take longer to mix back into the places where new stars are born. Galactic motion, turbulence, stellar feedback, and gas flows all help determine how enrichment becomes distributed. This is one reason the same kind of event can leave uneven chemical traces. A rare merger can strongly enrich a local region without immediately changing the whole galaxy. Over time, many events and many sources blend together, but the earliest and most metal-poor stars can preserve signs of uneven enrichment. The heavy elements in a planet are therefore the end result of both nuclear production and galactic transport. Making the atoms is only the first step. Delivering them into the next generation of matter is another. Future observations are the way this unfinished account will sharpen. More gravitational wave detections will improve estimates of how often neutron stars merge. More kilonovae observed across optical, infrared, X-ray, and radio wavelengths will show how varied the explosions are. Better infrared telescopes will be especially important because heavy element-rich ejecta often hides much of its energy at longer wavelengths. Improved gravitational wave detectors may reveal the merger and post-merger phases more clearly, placing stronger limits on neutron star structure and remnant lifetime. Laboratory nuclear physics will also matter, because models of rapid neutron capture depend on properties of unstable nuclei that are difficult to measure. The subject is therefore not only observational astronomy, it also depends on nuclear experiments, theoretical calculations, and simulations that connect small-scale reactions to large-scale light. Each new event can reduce uncertainty, but it may also reveal more diversity than the first example suggested. That is expected. A mature account of kilonovas will not be built from one perfect template. It will be built from many imperfect detections arranged into a population. The deeper importance of the first kilonova is that it changed the problem from speculation into measurement. Before the merger was observed, neutron-star collisions were a compelling sight for the R process, supported by theory, but not by a complete event seen in gravity and light. Afterward, the question became quantitative. How many mergers occur in a galaxy over time? How much mass do they eject? Which elements dominate? How early do they appear? How far does the debris travel? How do their yields compare with rare kinds of supernovae or other possible R process sources? These are harder questions, but they are better questions because they can be tested. They keep the conclusion grounded. Kilonovas are not just dramatic endings for neutron stars. They are part of the chemical work by which galaxies become able to build complex planets. Yet their role must be weighed carefully against the full history of stars, gas, explosions, and time. The event near NGC 4993 gave one clear answer and several open ones. It showed a neutron star merger producing the light expected from heavy element formation. It connected gravitational waves to gamma rays and to a rapidly reddening glow. It linked the motion of collapsed stellar cores to the origin of rare nuclei. What remains is the balance sheet of the cosmos, the careful count of sources and yields across billions of years. That account is still being assembled. Every future kilonova will add another line to it, sometimes confirming the first event, sometimes widening the pattern. The science is strongest when it holds both sides together, the confidence that such mergers can forge heavy matter, and the patience to learn how much of the universe is heavy matter they truly made. In the end, the story of Kilonovas rests on a quiet exchange between destruction and assembly. Two neutron stars reach the last point of a long orbital decay, and in the brief violence of their meeting, matter that was once locked under extreme pressure escapes into space. The event is short, but its consequences are not. A ripple in space and time crosses millions of light years. A flash of gamma rays marks the first release of high-energy light. A fading glow shifts from blue to red as newly formed heavy nuclei shape the path of radiation. From these separate signals, a single account forms compact stars collide. Neutron-rich debris expands. Radioactive decay powers the light, and some of the heaviest elements in nature are made. The discovery does not turn the universe into something simple. It gives one part of it clearer edges. Kilonovas are now known places where heavy matter can be forged. But their full role in the chemical history of galaxies still depends on careful counting, better instruments, and future events. That uncertainty is not a failure of the story. It is the space where the science continues. Each new detection will add detail to the balance, showing whether the first observed kilonova was typical, unusual, or one point in a wider range of outcomes. For now, the lesson remains steady. Some of the rarest atoms in planets may begin in moments that are almost impossible to see directly, revealed only when gravity, light, colour, and time are read together. The collision fades, the debris spreads, the signal passes Earth and moves on. What remains is a calmer understanding of how even the densest endings of stars can become part of the long material history from which worlds are made.